Hi and welcome to Maths class. In this video we're going to be looking at approximating the distribution of the sample proportion. Now that word approximating, we've seen that before when we looked at the binomial distribution being approximately normal when n was very large. And we've got a similar situation here. When we're taking samples, in reality, two things usually happen. First of all, we usually have a constant value of p, the population proportion. We don't often take samples when our population is small. We examined that in order to explore the theory behind the way this works. But in fact, in reality, if I'm doing an experiment or if I'm conducting research, I'm going to have a constant value of p. That's the first thing. And the second thing is usually I'm going to take a big sample because I want my results to be accurate. So I'll be taking a large sample. So let's have a look at what happens. Now, I'm just going to show you a different page. Okay, so what you can see there is I've got, I'm just using the example again of left-handed people. And my probability of success, if you recall, for left-handedness is 0.1. And in this case, I'm going to take a sample size of 100. Okay, so this is what happens. I'm just going to click draw. And I can see that my p hat in this case, which is my sample proportion, it looks like it's come in at 0.17. Yes, it says there 17 out of 100 successes. Let's do it again. Okay, so this time, now, so what I'm running here is an online simulator. It pretends that I've actually done this and it gives me some random answers according to the statistics given. So in this case, the number of successes you can see there is 9 out of 100. So my sample proportion is 0.09. Let's do it again. This time I've got 0.14. Let's do it again. 0.15. Let's run it again. Another 0.15. Run it again. This time I've got 0.13. Now I'm going to do quite a few in a row. And let's see what starts to happen. So I'm just taking a sample after sample after sample after sample after sample. Now, of course, in reality, I probably wouldn't do this. I wouldn't take multiple samples of size 100 because that might end up being too expensive or too difficult. However, if I know that other scientists or researchers have done the same research, I can look at their sample and I can look at my sample and I can collect it in this way. So far, I've taken now 25 samples. Let's have a look at the shape of that. Now, there are definitely some gaps, but I start to see a sort of peak in the middle. And then more or less, I've got some kind of symmetry happening. So now this is getting a bit boring. I'm going to increase the number of samples. I'm just going to go 100 samples and let's see what we get. Okay. Now that is starting to resemble my normal distribution. 100 samples is still not enough for it to really resemble my normal distribution. But if I keep going, let's take another 100, another 100, another 100, and so on, and so on, and so on. Okay. What about, let's do this again. Let's reset. What about if instead of 100, my sample size was 1,000? Let's start with 100 samples. Another 100, another 100, another 100, another 100. Let's do multiple, multiple, multiple. Okay, it's got a very determined peak there, which I didn't anticipate, but that is right, very close to the actual value of that the peak would be. Let's reset that and do it again. It's looking quite different. So we can see that something different happens every time, right? It's not going to be the same each time, but what I can see is a shape there that is approximately normal. I say approximately because it's not normal, right? It's just close to normal. But the bigger my sample size, the closer it's going to be. And the larger the number of samples that I take, the closer it's going to be. Okay, so now what we're noticing here then is that my distribution is looking symmetric. Let's look at where my center is, right? If I look at the center there, I can see that 0.1 is approximately the center of my distribution there, all right? In fact, let's go back to when we had 100 because I could see it more clearly then. Let's reset. Okay, In this example, you can really clearly see that 0.1 is my peak. It doesn't always work exactly that way. Let's try it again. 100 samples with a sample size of 100. This time 0.1 is not my peak, but it's still more or less the middle of my distribution. Okay, so 0.1 in this case is my expected value. It's my mean. So let's take some notes on this. I'll get rid of that. And let's have a look. Oh. Okay, so when n is large, I've got p hat being approximately normal, and my mean is mu, which is p itself, and my standard deviation, in fact, looks very similar to what we saw before. It's the square root of p times 1 minus p over n. But this is an approximation, so one of the things you've got to recognize is that this is going to give me approximate values, and also you've got to be able to recognize it in the question. So let's look at this question. We know that 30% of lily-pilly trees in a certain area are infested with a pest. Using the normal approximation, find the approximate probability that in a randomly selected sample size of 150, more than 35% of trees have the pest. Now, you might be wondering, what's a lily-pilly? That's a lily-pilly tree. It's an Australian native, and they do get infested by pests, but they're very pretty. So let's have a look at this question. I can see here the word normal approximation. So I have been explicitly asked to use the normal approximation, but it also says find the approximate probability. So again, we're going to use the normal approximation. So the information that I have is that I know that P is 30%, 0.3, and I know that my sample size N is 150. So what am I being asked for? I'm being asked for the probability that P hat is greater than 0.35. Okay, now I'm going to use the normal approximation, which means that I need to know my standard deviation. So my standard deviation is going to be the square root of P times 1 minus P over N. And in this case, that is square root of 0.3 times 0.7 divided by 150. Pop that into your CAS calculator, and I'm going to get 0.0374. Okay, all right. I also need to note that mu is going to equal p, so that is going to be 0.3. So my mean is 0.3 and my standard deviation is 0.0374, and I'm using p hat as approximately normal. So now I just go to my CAS calculator and I'm going to show you that. Just give me a moment. There it is, my old friend. Let's go into main. We're going to interactive, distribution. We're using a normal approximation. Normal is a continuous distribution. And we use the CDF because we've got a greater than sign there. And so now, what's my lower and what's my upper bound in this case? In theory, my lower here is negative infinity. Oh, sorry, this is a greater than. So my lower bound, in fact, is 0.35. I'm looking at being greater than 0.35, and my upper bound is infinity. My standard deviation I've worked out is 0.0374. And my mean is 0.3. That's the same as my value of P. Hit OK, see what we get. All right, 0.0906. Now I just want to show you, because what we're looking for here is we're trying to work out what the P hat value is. P hat is my sample proportion. Actually, in theory, P hat should be between 0 and 1. It's a fraction. My numerator is going to be the number of sample items with the attribute, and my denominator is the total number in the sample. It's going to be less than 1 and more than 0, or equal to 1 or equal to 0. So if I change infinity here to 1 as my upper bound, look at that. It does not change at all, because in fact, although this is in theory a continuous curve, by the time you hit x equals 1, that function is so close to the curve that the area after that makes absolutely no difference, at least to this many decimal places. So it doesn't matter to us. So I could have typed in upper bound is 1, and that would have made logical sense to me because I'm talking about a sample proportion. So let's write it down, 0.0906. Where's you gone? There it is. Equals 0.0906. The question didn't say, but let's go to 4 decimal places. Okay, that's how we do our worked examples. That's all you need to know from this video.